Hi folks, Essex Electrical Training here. One of the things that we get asked about a hell of a lot is if you're on your course, you're going, everything is DC, you know, resistance and all that, everything's DC. It's a step up when you're learning about AC that some people find difficult. So here's AC explained really quickly. Michael Faraday, the father of everything we know, he asked himself a simple question. He said, if we've got a magnet, then the magnet draws a pin in. It's not magic, it's not sorcery. There must be something between the magnet. There must be something there. If I turn this round, you can see there's two magnets there and I can't force them together. There's something between them that's stopping me from putting those magnets together. If we put it onto a horseshoe magnet, there's a horseshoe magnet, the old cartoon magnet like that, there it is, usually has red ends and like that, and it's usually, in the old cartoons, it's usually black. Well, basically what he said was, if I put a pin here, then the magnet draws the pin in. There must be something between the magnet and the pin, and there is. It's called magnetic flux. It's like an invisible jelly that runs all around any magnetic source. If I get a pin or a conductor and I pass it through the lines of magnetic flux, I generate an EMF. It's as simple as that. I generate electricity. You generate electricity. Here, another demonstration of magnetic flux. There's a coil in here and it generates magnetic flux all around that iron rod. So there it is. There's magnetic flux around there. I've pressed the button, the coil's on. You can't see it, you can't taste it, you can't smell it, but there is magnetic flux there. How do we know? Because the AC is going on and off. Like here, I'm passing the conductor through the magnetic flux. With AC, the magnetic flux is passing through the conductor. And so what you do is you generate an EMF, even though there's no connection between the iron rod, the electrical connection, and the windings. Let's take it a stage further. Let's now look at a field magnet. So there is a field magnet. There is our north, there is our south. There the two lines of a magnet. Let's just imagine that's like that. Okay, so you will have a magnetic flux that's going between north and south. There it is, always flows from north to south. Now I'm going to put a conductor in that magnetic field. So there's the two field magnets. I'm going to put my conductor there. Here we are, and it's just doing nothing. Well, on the field magnet, as I rotate that magnetic, the conductor around a magnetic field, then basically here it's glancing along the lines of magnetic flux. There's another demonstration. Let's go back to our horseshoe magnet. Generating electricity. Generating less electricity because you're not cutting the lines of magnetic flux at 90 degrees. So here you're generating almost nothing. Here you're cutting the lines of magnetic flux at 90 degrees. So you're generating its maximum. If we rotate this conductor around the magnetic field, this is how it goes. It's generating nothing. Increasing maximum, decreasing 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 nothing. The sine wave. AC rises and falls. It's not like DC. It's not like it's just in a flat line. It's rising and falling. So let's now take it a step even further. Let's say that we've got a coil. What is a coil? Well, if I have a wire from here to the end of this board, then I've got a wire. Let's say I put my hand on it and I ask you to tell me when I raise the temperature of that wire 2 degrees. You won't be able to tell me because it's, there's minimal effects in a long wire. However, If I get that wire and I wrap it around my finger into it, it magnifies all the effects that's taking place on that long light in a very small area. You'd instantly be able to tell me that it's raised 2 degrees just by holding the palm of your hand. So what we'll do is we'll take a coil. There's a coil. Let's say, doesn't matter what it does, let's say that it's just an ordinary coil. Let's say it's an electromagnet, it doesn't matter what it is. So what we are looking at this coil in relation to AC. So let's say that we are in this position. We are in this position. There's nothing being generated in that coil at all. It's no EMF, no current, no nothing. Now what we do is we'll go forward to this position. We are here. So therefore there's current now flowing through that coil. Faraday again said, if magnetism produces electricity, then electricity will cause magnetism. It's unavoidable. So when current starts flowing through that coil, you get magnetic flux around the coil. Brilliant. So let's go to the next period of time. We are here. We are here. There's nothing being produced again. So that magnetic flux collapses. So instead of me passing a conductor through the magnetic flux is passing through a conductor because it's nothing generating it. It's shrunk and it generates an EMF. Let's say, just for instance, I'm magnifying the figures to demonstrate a point. Let's say that EMF produces 1 amp. So the coil, let's say it takes 10 amps for all its life. That's what it's taking. But now, because of that collapsed magnetic flux, then it's generating an additional 1 amp. Okay, so now we go forward to the next period of time. Ping, up it comes. We are here, full current flowing. But wait a minute, we've generated another 1 amp. So now there's not 10 amps in that coil, there's 11 amps. So now we go forward to the next period of time. It collapses again, but this time it's 11 amps that's collapsed. So therefore we're going to generate more of an EMF. Just to demonstrate a point, let's say that we produce 2 amps. We go forward to the next period of time, up it comes, but now there's more current in that coil. So now let's say we're producing 13 amps. There's the current running through. We go through to the next period of time, it collapses, generates an EMF. All the magnetic field is getting really dense now because the current is rising. So as that collapses, now let's say it collapses and produces 4 amps. So now we've not got 13 amps in that coil, it's 17 amps. So that can't be the situation. Nothing would exist on AC. The coil in these fluorescent lights would just burn out. A motor would just speed up and burn out. That can't be the situation, and it's not. Charles Lenz's law. Charles Lenz stated that an induced EMF produces a current will oppose the cause producing it. In other words, if the current of the coil is going that way, the induced current will flow against it. It will oppose the current. Together with the resistance of the wires, it will impede the current. It is impedance, Z. That's why in AC, we don't say R for resistance, we say a combination. Z is a combination of the resistance of the windings, if you like, and this magnetic opposition. And we need the magnetic opposition or nothing would exist on AC. So, what does that mean that you get confused with in your principles classes? What does that mean? It means that, as I've said, we've got, let's say that we've got pure resistance that way. There's resistance. So that is resistance, DC, no magnetic opposition. But then this induced magnetic opposition is called reactance, and that is represented by X. It holds the current back. It impedes the current. So therefore, XL, inductive reactance. It's a coil, so it's inductive. It lags behind the current lags behind the voltage by 90 degrees. very, very briefly, what we're going to in future lessons is we need to combat this. We need to get rid of this inductive reactance because we want to be up here. We want to be in pure resistance. But instead, we are here. This is impedance. This is the resistance of the windings and the magnetic opposition. We want to get rid of that magnetic opposition, and we do that by putting in capacitance. XC, capacitive reactance. That lets the voltage, that lets the current through and holds back the voltage. So it has the opposite effect. But what do? Let's look at it in practice. So there is, I'm going to cut all this out. So look at this in practice. Here is a fluorescent light. There it is. So if I turn this on, there comes, and on the fluorescent light comes. You'll see on here that there it says it's 242 volts. That's what we're taking. Well, they take us out and shoot us if we mention 240, but we are actually on 240, not 230. And this fluorescent light is taking 0.75 of an amp. Now, this has got a coil in it, inductive reactance. So therefore, I've not put any capacitance in it at all. So that's why it's taking 0.74 amps. This is the power factor correction capacitor. It has the opposite effect of inductive reactance. So therefore, it's out of the circuit at the moment and it's taking 0.75 amps. If I put the capacitive reactance in, there it is. Now we're taking 0.37 amps. The power factor is at 0.8. Take it out, the power factor is at 0.45. But look at the actual fitting itself. There is the reactance out. There is the capacitor in, capacitor out, capacitor in. There's no effect on the tube at all. So therefore, it's running inefficiently. So we need to correct this inductive reactance, and we use that using capacitors. AC.